Previously, we talked about a binomial distribution. Here we have three histograms for a binomial distribution with different sample size. The first one, the sample size is 5. The probability of success is 40%. Second one, the probability of success is the same. And third one, but the sample size has changed from 5 to 12 and then to 25. And as you can see that the graph, the histogram, of course, because the sample size is 5 for the first one, and then we may have, say, 0 success, 1 success, 2 successes, 3 successes, 4 successes, and 5 successes. So for each one, we have a histogram. But if the sample size is 12, then we're going to have to go from 0 to 12. And if it's 25, I'm going to have to go from 0 to 25. That's why we have more intervals. And when we increase the sample size, the graph looks more and more like a bell-shaped graph, and which is normal distribution. So in the next slide, you can see when we have a lot of intervals, we have a curve. That's the normal distribution curve, and the histogram, those rectangular bars, are the probabilities for a binomial distribution. But as you can see, it's very close. There's a little bit like gaps, but you can see it's very close. So there is a theorem that we have for a binomial distribution with a large sample size, and usually if it's, say, greater than 15, but the bigger the better, the binomial distribution can be approximated by a normal distribution having the mean m times p. This is the formula we learned before for binomial distribution. Population mean is sample size times probability of success. And standard deviation is sample size times probability of success and times the probability of failure, and take square root. So this gives us way to calculate to find the probability for a large sample size of a binomial distribution, instead of using a binomial distribution formula, which it can be very tedious, because if you say you have 150 people and babies, and what's the probability that the number of babies, we have more than 67 babies watching TV, and more than 67, you have to do 67, 68, 69, and so on, all the way to 150, which is very tedious. By using this, we can use easily to get probability by using the binomial distribution. And the other thing, we notice that there's restriction here, condition that the sample size times p, which is the population mean, we want it to be also large. In other words, p, we want a p not too close to 0, not too close to 1. So the probability is somewhere like 40%, 50%, 60%. So we don't really want to do use normal distribution to approximate binomial when probability of success is too close to 0 or too close to 1, such as 0.1 or 0.9. So this is a theorem that we will not prove it. We're just going to assume this is true and we use it. So how do we approximate a binomial distribution using a normal distribution? We kind of have to do a little bit of change, because binomial distribution is discrete. The numbers are whole numbers, 0, 1, 2, 3, 4, 5 successes. But binomial distribution is not discrete. It's continuous. Like you could have numbers 0.1, 0.2, or 6.7999. So what we do is we're going to do what we call continuity correction. So here we have, say, x, and say let's 9. You can add half to 9 to get 9.5, and reduce by half to get 8.5. And look at this shaded area. And this shaded area, and it's going to be very close to, if we draw a graph, let me draw this picture here for you to explain the idea why we can approximate. So suppose we have a bell-shaped graph, and let's say we have x here. And remember, for binomial, each because it's discrete, so you will have like those bars at everywhere. And so at x, if we draw a bar, that's the probability density. So we draw a bar that's gonna sort of look like this. You know, 1/2, 1/2. We make the interval length equal to 1. And compared to so this area of this rectangular shape compared to the area under the curve. So we extend it a little bit further. And the area under the curve include here, 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 under the curve. That's the normal distribution. Compared to the area of the rectangle. As you can see, this little corner right here is not included in rectangle. So we're missing that part. But this rectangle includes that little corner there, which is not under the curve. So these two pieces kind of like cancel each other. So the area under the curve, shaded in blue, is going to be very close to the area of this rectangular bar. So that's called continuity correction. When we next we're going to look at a particular example. Suppose we have, let's say, 150 baby. Example, this is example 9 on page 245. Say we have somebody has done the work, a statewide survey, and concerning television viewing by children. So they found out about 40% of children, babies of a few months old, were reported to watch TV regularly. And so let's say that's the probability. If we call so watch TV is 40%, which means so in the whole state Ohio, the whole state, that somebody have done a survey, and out of all the babies of a few months old, we found out 40% of them watch TV. And which means if you randomly select one baby, there's 40% chance this baby watches TV regularly. So now we have a sample size of 150 baby. Suppose, say in a random sample selected from Ohio, we have 150 baby randomly selected. That we want to, so we have a variable x, which means the number of babies watch TV, the number of babies watching TV regularly. Now, the first question is, we want to find out what is the probability that x is between 75 and 52 and 71, both inclusive, which means x is greater than or equal to 52 and less than or equal to 71. And we know this is a binomial distribution because every baby either watches TV or not watches TV regularly. And we want to, if we want to do it by binomial distribution, we have to find out, okay, what's the probability that 50 out of the 150 babies, 52 babies watch TV, and then plus 53 babies watch TV, plus 55, plus 56, all the way to x equal to 71. So that would be about like 20 cases that we have to do. And which is, and for each case you have to use that formula, n choose r and p raised to x and 1 minus p raised to x for each x value here. So plug in for each one, and that is just too many cases that we have to do. But the good thing is the sample size is large. So using what we just discussed previously, that this theorem, that if the sample size is large, 150 definitely is large, and the probability p is not too close to 0 or 1. It's 40%. It's somewhere in the middle between 0 and 1. And we can approximate this. Instead of using rectangular bars, we can choose a bell-shaped graph to treat it as a normal standard deviation. Normal distribution. So when I do this question, but we have to do a continuity correction. What we do is, so we're gonna, for the upper bound 71, we're going to increase it a little bit to add a half to it, 71.5. For the lower bound, we're gonna reduce it to 51.5. So originally we're supposed to have between 52 and 71 these many cases, but we add a half to it. We got 71.5, and decrease 52 the low bound to get 51.5 to make sure we include 52 and 71 in there. And so now this can be treated as a normal distribution, which we can do it the way we talked about in chapter 7, the normal distribution. So we first convert x to z by using the formula. And we know the formula converting x to z is x minus mu divided by sigma. But before we do that, we have to find out what mu and sigma is. And we had a formula before for binomial distribution. Mu is equal to n times p. So in this case, n is 150 times p, which is 0.4. That gives us a 60. And sigma, the formula is square root of n times p times 1 minus p. So which gives us square root of 150 times 0.4 times 0.6. And you can use the calculator, we'll get 6. And now we can plug into the formula now. So we convert x to z by plugging numbers into that formula. So this x would be the x value corresponding to that x, 51.5. Subtract the mu, and mu is 60 minus 60. Divide by sigma, sigma is 6. And less than or equal to, and let's convert the upper bound also to the corresponding z value. Notice that both of these are x values. So x is either this, between this and that. So we're going to have to convert both numbers to the z value, z score. So subtract the mu, divide by sigma. Now we can use the calculator to work out both numbers. That will give us, let's say it's negative 1.417. Less than or equal to z, less than or equal to 1.917. And again, this is using converting the x to standardized variable z value. Now we can use this normal distribution table to do this. So remember, we are looking for the area, the probability of a normal standard deviation. Normal distribution is going to be between the area under the curve between these two values. So this is the area we're looking for. And remember, to find the area in the middle, we're going to use the table to find the area to the left side of 1.917. So when you look into the table, I'm just going to copy this from the book, you will get 0.9724. which gives a total area starting from here all the way to the left end. That means it includes this area. So we need to find out the area of this part, the left area to negative 1.417. So we look into the table and we found 0.0782. Again, you are using the normal standard distribution table, which is in appendix, the table 3. And now we subtract them, we're going to get 0.8942. So that gives the area in the middle. So that tells us, go back to the original question, and we're going to find, so there's almost 90% chance that 90% of the babies, the 90% chance that out of these 150 babies, there will be the number of babies that watch TV will be are between 52 and 71 inclusive. So there are that many babies. 90% you have this many babies watching TV regularly. Similarly, so this is an in-between case. Similarly, if we do